slow day. I didn't really feel like coming to class. It is rainy. You want to sit at home, like drink tea or coffee or whatever, or beer. Whatever suits you, huh? Yeah, you have that option, but I don't. I have to come. I'm thinking of doing all of my classes from now onwards, like till the end of time, like this. Like it's just a camera, right? For me, it's not gonna cost anything, but it's gonna be helpful to the students, I guess. Okay. So we have to move a little faster today because there are some things that we want to cover from the background that we didn't go over. We forgot to go over. So we have to move faster to get to the topic that we want to cover in this lecture. Okay. From the background, we want to talk about the different coordinate systems you can have. Right. Let's say this is your aircraft. You can have three different sets of coordinate systems. One is based on the Earth surface, which we call the Earth-based coordinate system. This essentially means that your XY plane is always parallel to the surface of the Earth, right? We call this coordinate system XE, YE, ZE, right? So the XY plane is essentially the same plane as the XY plane on the Earth's surface, and Z is always perpendicular to the Earth's surface. The other coordinate system that we are going to use here is the body-based or aircraft-based coordinate system. Okay, so in an aircraft-based coordinate system, your x-axis passes through the aircraft plane of symmetry and the center of gravity. And it is on the line that connects the center of gravity to the nose and the tail of the aircraft. Okay. Essentially, it is on the chord line of the aircraft, right? The x-axis. And the rest of them you can figure out. They have to be yes. It moves with angle of attack, yeah. Airspace, no. And this third one is going to be called the air path based coordinate system. So based on these three different coordinate systems, we define 6 different angles, right? The idea was the airspace system is your fixed coordinate system, if you will. Like it doesn't rotate, it doesn't do anything, right? All of the other coordinate systems move, rotate. So we can have the angles that this coordinate system, I'm going to call that the Earth-based coordinate system x of E, makes with x of A, the Earth path coordinate system, and the Earth-based coordinate system, the angle is air-based coordinate system mixed with the aircraft-based coordinate system. If we're gonna have an angle psi here, which is the angle of yaw. Okay. What else did we have here? Theta, angle of pitch, and then phi, angle of roll. So these are the angles that your body makes with the Earth-based coordinate system. The coordinate system of the body makes with the Earth-based coordinate system. But there are three other, I think we mentioned these, but we failed to mention, I failed to mention the angles we have here. Pardon me? Gamma. No, let's do this. We did introduce the angles, but okay, gamma. Since I don't want to make any confusions for you, let's go over them. What were the gamma, alpha, and theta? Okay. So just one of them was part of these three angles, right? Because you are looking with angles XE makes with XA. Gamma, right? So that's the only angle that we are really interested at here. Okay. So here we are going to have three different angles, as I said. First one is called the azimuth angle. I always have problem pronouncing this one. It's called the angle X. And then we have the flight path angle, which was the angle gamma that you mentioned. So that angle XA makes with X of E. And then we have finally the aerodynamic roll angle. We also have the angle of attack alpha and angle of the side slip beta that we are already familiar with. So coordinate systems and angles. Any questions so far? That's the angle between X of E and X of A. So you're essentially think about it this way. If you are moving, your flat turn has some yaw, right? If instead of moving the aircraft in the yaw direction, you are changing the air path, you're going to have some azimuth angle. Okay? So let's go back to the discussion we had here. Where did we stop? At the flat turn, right? Okay. So let's try to find the equations of motion for another type of flow or another type of flight. Sorry. And this one is called the steady non-slipping, non-side slipping banked turn. Okay. So the first thing we need to address here is what is a bank term? What is the difference between a bank term and a flat term? So essentially, the difference is that the flat term, you had some yaw, right? Here, we don't have the yaw anymore. We have the roll, right? So the angles that are really present here are the flight path angle, right? And the aerodynamic roll angle. Combination of these two is called the bank angle. How is this bank angle related to flight path angle and aerodynamic angle? Is through a sine relationship. Sine of phi is equal to sine of mu multiplied by cosine of omega. We have a lot of phi's. Let's make it a capital phi, just to make sure we don't confuse. So your bank angle is the capital phi, which is equals to the sine of that bank angle is equals to, and it's called the angle of bank. Well, let's try to find the equations of motions for this for this specific type of flight. So study non-side slipping bank term. How many equations should we have here? We are moving like this, right? So how many? 3, exactly. So all of the 3 equations are going to be present here. So let's come up with the equations in all 3 directions. And like, I want you to jump in and contribute. Essentially, tell me what the equations are. Okay. Negative drag. What else do we have? T sine. Me neither. So what should be the angle here? What is the component of? You don't need to use the angle of bank, right? T sine of alpha t, right? Cosine or cosine or sine? You said cosine. Yeah, that's correct. Cosine of alpha t, right? What else? Just a quick note from the mathematics. Whenever you were confused about cosine and sine, since we are dealing with a small angles of attack, right? You will give cosines to the direction that you expect to have the major contribution of that force, right? You expect to have the major contribution of thrust in the drag direction, right? So cosine. What is this alpha? Who can tell me what the alpha t is? Alpha of t. So that's what did we call this alpha t? Angle of thrust. So that's exactly. So this is actually dictated by your thrust vector. What else do we have here? What else do we have here? We have a component of weight. Exactly. What is it? Is it a component of weight or is it the full weight? Is it negative or positive? Negative W what? Sine of gamma. This, you don't need to use the bank angle, guys. This is just an introduction, right? Okay, so this is one equation of motion in one direction. Okay, let's go to the next one. We don't have a slip. We need C. Okay, is it negative or positive? Negative C. In the Y direction. So this is, let's say this is your aircraft. This is the Y direction, and this is Z, right? This is the most common things that we use in the three-dimensional case. So lift is going to be mostly in the Z direction, but you brought up a good point. Do we have any components of lift here? Okay, we should. So tell me what the equation is. A sign of okay, let's think about it a little bit. What was the general form of equation? Let's go back to the general aerodynamic equation we had. What was the equation? What was A of Y? Aerodynamic forces in the Y direction. Okay. So did we have any contribution of lift in that direction? So we don't have lift here. But what did we have? What is sine of beta here? Is 0. Okay. So the only thing we really have, the only things we really have is weight and your centrifugal force here. Okay. So based on this, what is the equation? So we have W sine of omega somewhere. So this has to be W cosine of omega, right? W cosine of omega. That's the component of, okay, because we have a flight path angle, right? So omega will change you will have components of weights in the direction in XA versus XE in that coordinate system. But also XP is also different from XE. So W weight is going to have a component in that direction as well. Not another W, right? Okay, I think we are still confused here. Then how should we do this? It is very hard to draw a three-dimensional thing on the board. But so this is your X of A, Y of A, and Z of A. Okay. Let's say this is your x of E, Z of E, and Y of E. And then we have x of B, let's do Y of B like this, and then Z of B. Okay, we have three different coordinate systems. What is the direction of weight? ZE, right? So this is where you have the weight direction. Okay, so what is the angle we're gonna get? What are the angles? The angle was the angles between E and A, right? So we're gonna get the angle omega is going to be the angle between YE and YA, right? So what is this? This is already confusing. YE and YA, right? This angle is going to be your angle omega. And what other angle do we have here? Or angle gamma? Why do I say omega? What other angle do we have here? Aerodynamic roll angle, which is the angle between ZE and ZA, mu. Okay.
So is the angle between, for example, XA and XE different than YA and YE as far as Greek notation?
That's the idea, right? In each direction, these angles are different. That's why I mentioned these were representatives of your coordinate systems, not the axis. Coordinate. So based on this, angle of yaw is going to be the angle you're going to get for the x-axis. Angle of pitch is the angle you're going to get in the z-axis, right? And angle of roll is the angle you're going to get in the y-axis. Or, I'm sorry. This is y-axis, this is x-axis.
At least last class, like XA and XE and then XA and XB. Where gamma alpha.
It was a two-dimensional thing, right? That was different notations. That was.
Oh, so this is like that.
Yeah, it is a three-dimensional. This one is a three-dimensional. Let's actually do this because I think it is very hard to avoid confusion here, right? But so before like going down the rabbit hole here, as we did last lecture, just look at it this way. We have these two angles. There is W in one direction, right? And we have these two axes in the other component. This W is going to have a component on this and this. That's it. That's the idea here, right? And one of the components is a direct component, which is why you only have sine of omega. But one of the components is actually going to have components in other two directions, right? So it is like saying that this, in a three-dimensional case, let's say you have this vector, right? Let's say I find a projection here, which is going to be W cosine of this angle, right? And let me delete this. And if I want to find the component of this W cosine of theta on these two axes, your component is going to be, let's call this theta 1. The component of this on this is going to be W cosine of theta 1. Component of this and this is going to be W cosine of theta sine of theta 1, right? So this is what we are seeing here. We have one component in the x direction of for W, and then the other component, which is going to be W cosine of omega, will have two other components in the Y and Z direction. Does it make sense? No?
Is that plus or minus?
Which one?
Right?
We were actually going to determine that, right? So your W is going to have two components present, three components present. One is the direct component of W. These two are, let's call them indirect components of W. Okay? So these two will be present. Hopefully we are avoiding confusion here. But again, it's a three-dimensional space. We have a lot of three different coordinate systems that are on top of each other. I understand you may be confused, but as long as you understand the main equations, you should be fine. Our main focus is on the two-dimensional axisymmetric flight, right? Which is usually the main focus when it comes to flight mechanics. But we will talk a little in a little more detail in orbital mechanics part of the class. And hopefully over there you will have less confusion because there are a lot less forces involved there. Okay. So where were we? We have, let me actually give you the equations and just move on. We have a positive component of weight here, and then we have a component of the centrifugal force, which is cosine of mu. For the force in the other direction, we have the component of thrust, alpha T. You have the lift, you have the weight, and we also have the other component of centrifugal force.
I think where I was getting confused was like which Greek letters meant what. Which I've been trying to overlap other stuff.
Okay, so are you still confused or?
A little.
So there's,
Theta means angle of pitch, but we also define theta as between xb and xe. So is pitch the angle between xb and xe, or are those separate angles?
pitch angle between XB and XE. XB and XE, you have theta angle of pitch here. And what else did you say?
Well, yes, I'm just wanting to know if like the angles between the reference axes are those the same thing as yaw pitch and roll, if they're the same Greek letter. Like flight path is gamma, so is flight the angle of flight path also the angle between xa and xe.
Yes, that's, but X, not XA, ZA and ZE.
Okay, so it matters which axis.
That's correct. That's why. So I shouldn't have used X. This book that I'm using uses X. This refers to the coordinate system. So this whole thing, E, let's call it EA, right? EB, and this refers to the axis, the corresponding axis. So angle between Y of E, Y of A, Z of E, Z of A. Okay? Does this answer your question? 100%. Okay, that's good. Okay, so the last thing we want to talk about here, and then we want to move on to the two-dimensional or the axisymmetric, for the symmetric flight, right? The accelerated symmetric flight, which is going to be the focus. The symmetric flight is going to be the focus of the flight mechanics in this course. Is the flight with variable mass. Would you mind if I clean this part of the board? Yes. You will be a lot more confused because we're gonna change the notations a little later. And I'm sorry about this, guys. Pardon me? Yeah, I'm sorry. This is, I don't know why, but they don't use universal notations for this. So, pardon me? If you can put them on your formula sheet, yes. I'm not gonna provide a formula sheet, but you can put them on your own formula sheet. Yeah. Think about it this way: you have like this many forces in 3 dimensions for 3 different coordinate systems. It is supposed to get confusing, right? There is no other way, right? That's why we are going to simplify it as soon as possible. So the steady flight in a variable mass situation. What does variable mass mean? What I mean is, how would you gain or lose mass during flight? You burn fuel, exactly. Propulsion. Yeah, you can lose payload as well, yeah. But yeah, so let's say your fuel is this part at time t, and at time t plus dt, your fuel is going to be completely burnt out, at least this part of the field. The velocity of plane here is v. The velocity of plane here is v plus dv. What is the velocity of this burnt section of the field? If you can, we are just lumping everything together. So let's say we have burnt the fuel and just throw it out. What is that velocity? If we throw out the burnt section with a velocity w, yeah. Yes. No, it is not gonna it is not gonna be in free fall because it doesn't start with velocity 0, right? It starts with velocity v, which is the same velocity as the plane's velocity, right? The exhaust velocity. So v essentially your velocity of the plane minus the exhaust velocity, whatever that exhaust velocity is, right? Velocity relative to Earth, velocity you see from the air. So let's say your exhaust velocity is w, right? The velocity of this is going to be v minus w, right? After time, here we have time t plus dt, okay? So how can we calculate the force here? Force is going to be derivative of mv with respect to t, right? That's the Newton's second law. T, time. Here, on numerator, mv. D parentheses mv divided by dt. Okay? Which is, this is that we all know that this is another form of Newton's second law, right? Okay. The changes in momentum with respect to time. This is actually how you get to the Navier-Stokes equation. So let's say the changes are linear, which means that we are going to get delta mv divided by delta t, right? So your situation here plus your situation here. And we are going to assume the mass of this burnt fuel is delta M, and the mass of the aircraft is M. So for time 2, you are going to get M, which is moving at velocity v plus dv, right? And you're going to get delta M, which is moving at velocity v minus w, right? This is the situation at time 2, at time t plus dt, minus, and this is still the numerator. I just didn't have enough space there. Minus the situation at time 1, which is delta M plus M multiplied by V. And all of this is divided by delta T, right? Okay, so if you simplify this equation, what you're going to get here eventually for force is going to be, F is going to be equal to M delta V delta T minus V or W delta M delta T delta M. Okay, and if you take the limit of this whole thing and take delta T to 0, you will end up with F equals to dV dt minus W dm dt. So you have to have the flow rate of the fuel leaving the aircraft as well as the rate of change of velocity with respect to time. And then come up with this new set of equations of motion, right, for this variable mass. Because we previously assumed that the mass is not changing.
Would the mass not changing be a viable assumption for like electric aircraft? Since we want to have.
Okay, so electric aircraft change weight based on the charge. It is. What is the weight of an electron? 10 to the negative, somewhere between 11 and 27, right? That it is. So essentially, the weight of your atoms are going to be very small, but you have like millions of them. But it's just gas, so you're not losing any fuel. So I want to say not only it's a viable assumption, it's a true consideration. It's not. It is not just an assumption. You can just like forget about the changes in mass. But you can actually, if your aircraft is heavy enough, you can forget this assumption here that you're losing fuel. Because these equations of motion that we have, these are the very general form of equations of motion, and these are in use, right? People use these in real design situations. So yeah, it is not losing any mass is a viable assumption in many types of flights. Okay, is there any questions? So let's change the topic a little bit. Let's go back to the Anderson's book, The Introduction of Flight. And we are going to do the chapter 5 of the book. Chapter 6. We have already started chapter 3. We have talked about the equations of motion. We just went in, I think, a little too deep in the equations of motion. Right? So let's back up a little bit. Let's try to simplify things. What we want to work on is symmetric flight. We want to find the equations of motion for symmetric flight, symmetric accelerated flight. Okay, so for a symmetric flight, your configuration will look like this. Let's say this is your chord line or the x of b, and this is your horizon. Horizon or x of e. And then you also have a flight path x of a, right? And there's also a thrust vector in here that comes into play. Okay. When you're dealing with this. So this is called, we're going to call this chord line here. We're going to call this flight path. And this one is already the horizon. We already know that. Okay, what are the angles that are present here? Something, I think, I don't remember who said it, but someone said it that the thrust vector is in the same direction as the chord line, right? Which is not true, right? It can be in the same direction as the chord line, but in general, thrust vector is an independent vector. It really depends on the formation of your jet, right? Okay, so what are the vectors we have here? Pardon me? Alpha of t, that's correct. Alpha of t is the angle between the flight path and the thrust vector. Okay, that's what we have already seen. We're already familiar with this. What is the angle between the chord line and the flight path? Alpha, angle of the attack. And what is the angle between the flight path and horizon? We used to call it gamma, but in Anderson book, Anderson calls it theta. Okay. Just have to make sure that from now on, in the Anderson book, theta is actually the flight path angle. We used to call it gamma. Okay. We are not going to do, since we are simplifying things, we are not going to use theta for any other things anymore. So if you were dealing with a like three-dimensional thing, theta has a previous definition. But if you are dealing with a symmetric flight, theta is going to be the flight path angle. Okay? Is this clear? Okay. And for most of the problems, you're going to be dealing with this symmetric flight, which is the easier type of flight, right? Okay. So let's find the equations of motion for the accelerated symmetric flight. And these are the equations of motion we are going to come back to again and again. Okay, let's do it. T cosine of alpha t. So which direction is this? X of A, exactly. So T cosine of alpha t. What else do we have here? Drag. Right? And what else do we have here? Weight. Okay. It is a component, right? Weight is in this direction, right? And we want to find the equation of motion on this line. So which component of weight do we have here? W sine theta, right? Let's do theta from now on, right? But you're correct, that we did gamma before. So what is this equals to? No, because it is an accelerated flight. Whatever the acceleration is, right? Just the acceleration, mass time acceleration. So what we are gonna do is that we're gonna assume mass doesn't change, and then dv dt, right? Okay. So let me actually write sign of gamma on top here just to make sure that these are from our previous notations. It should be sign of gamma. Yeah, mass unchanging. Different conditions. Right? Okay. We're actually going to go back to the variable mass in the future, but not now. Okay, so what is the equation of motion in the other direction? In this direction, right? In the direction of y. We are writing the equation of motion on x of a and y of a. T sine alpha, positive or negative? Okay. Alpha t. That's correct. What else? It really depends on how you're looking at it. So if you're gonna do minus lift, then these have to be minus as well, right? Yeah. So if you want to do plus, the point is they have to be in the same direction. That's the idea, right? And your weight has to be in the opposite direction. So what other component do we have here? Exactly. What? Yeah. So we don't have that anymore. Yes, basically on the, yeah. Okay. So what is it equal to? Bless you. It is not going to be 0. No, this is the velocity. This is not just a component. This is the velocity vector, right? So we are writing in the direction of the flight, right? So velocity only has one component. Rate of change of altitude. So there's acceleration. How would you? Climb rate. Okay. No, but interesting perspective. What is that acceleration, though? No. Okay, let's say we are exactly, we are already including gravity in the weight, right? But let's say dv dt minus gravity, right? What is that dv dt? So what is that acceleration? The thing is, let's think about it this way. We are not moving in the y direction at all, but we are moving in the xa direction, right? This is x of a, which is the direction of the flight, right? Which is y of a, which is not the direction of the flight. Yeah. Okay. There is no dvdt in this direction, right? There is no v in the other direction. But it is not. Is it? I don't know. I don't know. I'm asking you. So we have 1 for 0. You're okay. 2 for 0. Huh? You're for 0 too? 3 for 0. Pardon me? We are not. We didn't say anything about climb. We didn't make any assumption here. Climb, not fly. We didn't say anything about climb. Okay, let's say let's go back. Let's think about it. Just look at it from a macro perspective. Your aircraft is moving, right, in this direction. We want to find the acceleration in this direction, right? What is this acceleration? Centrifugal acceleration. That's it. Oh, that's it. V squared over r. mv squared over r. That's it. Exactly. M. Pardon me? I didn't understand your question. Why should we have dv squared? The thing is, velocity is not changing in this direction, right? Velocity is only changing in this direction. No, we are not making the assumption. We are not. We are never making an assumption about whether the Earth is flat or not. Think about this way. It's yeah. No, we are not making an assumption. You are welcome to make the assumption here. But the point is that the idea is this horizon is always in the same direction at the surface of the Earth, right? That doesn't really mean you are making the assumption that the surface of the Earth is flat. We don't really care because the aircraft is so small that it will see just a flat horizon. But we will come back to this discussion in the orbital mechanics because over there is going to be important. Okay, that's okay. This is not velocity in this direction. This is the velocity in this direction. That's the centrifugal acceleration. So if you are moving around as a center with the linear velocity, which is tangent to your direction of rotation, right, is r omega, right? Then your centrifugal acceleration is going to be v squared over r, right? Yeah. Okay. So we have the equations of motion for symmetric flight, for accelerated symmetric flight. But what if the flight is not accelerated? What will happen to these equations of motion? Yeah, that's all of it. The right-hand side is going to be 0. So what does it mean for the general equation? Okay, so essentially your T cosine of alpha minus D minus W sine of theta is going to be equal to 0. We can say the same thing about the y direction. But let's make it a little simpler, or not necessarily simpler. Let's make it a little more specific. What should be this equation of motion during a level flight, unaccelerated level flight? What does a level flight mean? A level flight means that you are not changing altitude, right? So what is the flight path angle? 0. Okay. So what does it mean for the equations of motion? T cosine of alpha t drag equals to drag, and then right. And if your thrust vector is very small, then we are going to see these familiar equations that we have seen before. The T is going to be equal to drag, and lift is going to be equal to weight for a level unaccelerated flight. Is there any questions? Okay. Hopefully we are not confused anymore about these new topics. Yes or no? Yeah, it definitely is much easier to visualize, right? I guess we need to create a 3D model to help with the visualization. Next year's. Yeah. I think that's a good idea. Yeah. Okay, so we are going to talk about, this is the equations of motion, this is the level flight equation of motion, but we are going to move on from the equations of motion, which I think is a relief for you guys. We are going to move on to the analysis of thrust and power and the effects of altitude on thrust and power, and then the general flight mechanics understanding of thrust and power. There is this concept called the thrust required. The idea here is that in order to keep the flight at a level flight condition, you need a minimum thrust, right? Less than that, you will lose your thrust condition. So, and we use TR for it, thrust required. If you write your equation of motion for a level flight, L equals to W, and we remember from the definition of lift coefficient, L is equals to QS CL, right? And then your thrust is equals to drag, which is equals to Q infinity SCD, but we don't really care about it here. So let me actually write it down. We do care about it. Okay, so what would be the ratio of T over W here? T over W. It will be the drag coefficient divided by lift coefficient. Okay. Then we can move weight to the other side. T is going to be equal to W divided by CL divided by CE, which is the lift to drag ratio. And this will give you the required thrust to maintain, a level flight. How do you think this will change with velocity? How do you think the required thrust will change with velocity? It should go down. So it will go down to 0. So at very high velocity, you don't need to have thrust to keep the level flight. For a while. Okay, what will happen after that while? Okay, so what will happen to the required thrust then? You go back up. Exactly. So there is a minimum value for the required thrust. You cannot get lower than this. And you get that minimum value at the maximum lift to drag. Okay. Can you repeat your question? Yes, but something that you are not seeing here is that burnt fuel, how much of the weight of an aircraft, not a spacecraft, of an aircraft, is due to the fuel, right? How much is that? Like 50% of an aircraft? Yeah, like full tank. 70% of the aircraft weight is fuel. Okay. Pass. I like your way of thinking. Yeah. Okay, so that's an interesting discussion to have. Well, let's finish this and then we'll come back to this discussion next week. I want to make sure that we cover all of this topic. But you're correct. If you decrease the weight, if you don't assume the weight is constant, then your thrust required is going to be less as well. But our focus is on its dependence on lift and drag, not weight here per se, because weight is a design parameter, right? And that it doesn't really change with velocity that much. Okay, so how does the lift to drag ratio changes with angle of attack? Do we know this? Okay, for the lift, you will have the stall condition after the certain angle of attack, which essentially means that your lift to drag ratio will get to the maximum value and then it will decrease as a function of angle of attack. Okay, this is just a reminder. Okay, so there's an angle of attack at which you are going to get the maximum lift to drag ratio. As you increase the angle of attack, your lift to drag ratio is going to change. So what does it mean for thrust required for the thrust required versus the angle of attack? What do you expect to see? What do you expect to see? Variation. What is the variation of thrust required versus the lift to drag versus the angle of attack, not velocity? For the lowest ones, you're going to get the highest thrust required because that's the lowest value of lift to drag ratio, right? And then as you increase the angle of attack, you are going to see the reverse pattern, essentially, increasing alpha. The reverse pattern compared to the flight velocity. So you start with a very high thrust required. It goes down, goes down, goes down until you get to the maximum lift to drag ratio. Then it will go back up, right? But it won't go as high as it was before.
Like at some point in level flight, like I said, you need more thrust because you're not having that lift component as high as with different angles.
You don't have the lift to drag ratio, right?
Yeah.
So we are at this part. We are having the minimum lift to drags. So your thrust required is going to be higher, right? As you go off, your thrust required is going to be smaller, but it doesn't go as down as before, right? It is not going to go be as small as before. Does it make sense? Okay. So let's see. Let's see if we can find the relationship to give us the lift coefficient or drag coefficient or some understanding of lift and drag coefficient for this minimum value. Okay. What is happening to that curve at that minimum location? What can we say? It is a minimum of that curve. Okay. And we want to find a relationship for lift and drag coefficient. Where can we start? What can you say about the minimum of a curve? The derivative of TR, exactly. With respect to V infinity is 0. So let's see if we can find a formula that relates to V infinity. From the equation of motion, we had TR is equals to D, which is Q infinity S CD. If you recall from the previous lectures, CD has a parasitic component and an induced component. Right? This is something that we have seen. We have seen it for an airfoil, for a wing, essentially, and we have seen this for the whole aircraft. Okay. Which one is this? What do you think? CR square, like that's the induced part of the drag. So this part, let's actually bring all of this in and do the Q infinity S. This part is called the zero lift. Thrust required. This part is called the induced thrust required. Okay. Well, from the other equation of motion we have, lift has to be equals to weight, right? Which itself is equals to Q infinity SCL, right? So we can relate CL to weight. CL is going to be equal to W divided by Q infinity S, right? We have CL squared here. So we're going to replace that with W divided by Q infinity squared. One of the powers of this denominator cancels out with this whole thing. And we are going to get W squared divided by Q infinity S multiplied by pi ER. Is there any questions here? The second part is the induced thrust coefficient. Let's go back to this plot again. Thrust required versus V infinity. The idea was it changes like this. And your zero lift TR, how does your zero lift TR change with velocity? The zero lift thrust required, this part. Does it increase or decrease with velocity? It's a function of Q infinity. It has a direct relationship with Q infinity. So how does it change with velocity? Well, it has direct relationship with V squared. So that's true. So how does it change? How? How would it decrease? No, I'm talking about its relationship with only the zero lift part. This part. Thrust required, zero lift is equal to 1/2 rho V infinity squared multiplied by CD naught, right? So it will increase, pardon me? Yeah, and the surface area, exactly, thank you. So it will increase like this. But the induced part has an inverse relation with the V infinity, right? So it will decrease like this. And the minimum lift to drag ratio is actually going to happen from the figure. We can guess that it is going to happen where the zero lift thrust required is equal to the induced thrust required. But we can definitely prove that. We should prove that. We cannot just take as this. How can we prove that? We just take the derivative of thrust required versus V infinity. Okay. If you take the derivative here, you're going to get, this is 1/2 rho V infinity squared, right? So this part is going to be rho V infinity, right? S CD naught minus, right? What is the derivative of 1 over V squared? So what is the derivative of 1 over x squared? Negative, so d of, is that it? It is going to be -3, right? Over x to the power 3, right? Yeah, I just want to make sure that we are all clear on this. Okay, so you take the derivative here as well. You are gonna end up with W squared divided by pi ER V infinity to the third plus S. That's it, right? And then from what time is it? Let's actually forget about the derivations. We are way behind, guys. You can eventually, if you do the derivation, let's actually do this as a bonus one. So derive this, the thing that I'm writing. CD and 0 is going to be equal to CL squared over pi E AR. What does it mean? It means that your path at this minimum value of the thrust required, at this minimum value where this derivative is 0, your parasitic drag is equals to the induced drag, right? Does it make sense? So if you give me the proof for this one next Tuesday, you will get a bonus one. And if there's no question, that's it for today's class. And yeah, that's it. No, not yet. I will post it. I'll post the homework either today or tomorrow. You will still get a week to submit the homework. So it will be like next Friday if I post it tomorrow. I will also give you the graded homework 1 next Tuesday. Yes. To derive this. Okay? The bonus is to derive this equation for the minimum thrust. That's it. And